Section 4.7 is antiderivatives. So a function f is called an antiderivative of another function f on an interval I if f prime of x is equal to f of x. And I should say capital F. So capital F prime of x is equal to f of x. So this capital F is an antiderivative of lowercase f, the other function, on the interval I if this is true for every x in that interval. And generally, the intervals that we'll talk about will often be the entire real numbers or just simply the domains of the functions in question. So we don't have to be too technical about the intervals for now. So consider how many antiderivatives the function y equals 2x minus 5 might have. Now, it is what it sounds like. The antiderivative of a function, it's sort of like taking the derivative of the function in the opposite direction, right? It's the function whose derivative is the function. So if I know the smaller function, I might be able to imagine a function sort of at a level up from it, who, when we take its derivative, is equal to my given function. So in this case, we're looking at, this is our lowercase f of x here, and we're wondering what it might have for an antiderivative. Well, it's probably easier to do this in two pieces, right? Let's consider 2x as its own little function and -5 as its own lowercase function. So 2x, well, we might recognize that as being the derivative of x squared. Right? Maybe with some guessing and checking, you could come up with that. It's probably not too hard to see that. We've done a lot of power rule derivatives by now, so we could see that we can go this direction as an antiderivative. And similarly for -5, well, the derivative of -5x is -5. So there we have it. It looks like, right, the powers of the x's involved increase by 1. This one was x to the 0, and it went to x to the 1 to introduce an x. Similarly here, 2x increased to x squared. X to the 1 went to x squared. And that's the way it would have to work if we're going to talk about an antiderivative, because of course, this thing's derivative has to be this. And if we're talking about polynomial type functions like this, well, then of course, the power is going to increase by 1, because if we go backwards, it's going to decrease by 1. Or if we go the normal way, it'll decrease by 1 thanks to the power rule. So one antiderivative we might come up with, calling this capital Y, or capital F of x function, the antiderivative of this function, might just be x squared minus 5, right? We just take these, or minus 5x. We just take these two things together and say, well, that's an antiderivative of 2x minus 5. And I can see that because it's really easy to check. I could just take the derivative of x squared minus 5 and see that, yes, I get 2x minus 5. So this, of course, is an antiderivative to 2x minus 5. But we don't just stop there. Unfortunately, if we consider this, here's another example. This could also be the antiderivative of 2x minus 5, can't it? Right? So if we look at it, this is 2x minus 5 and then plus 0. We have a constant added there. And we still have the same derivative, right? Y, capital Y prime here is still equal to our original function, 2x minus 5. And if you thought about it, this is true for any constant that we might ever have added to these functions. So that's how we write down our most general antiderivative, is we add a c to the end of it, and we just say c is some constant. And generally in calculus, Calc 2, and on for the rest of calculus, you'll probably just use the letter c, and you'll never really have to write down where, c is some constant, some real number. Not a function of x, of course, but some constant. So in other words, a value whose derivative, of course, is 0, because the derivative of constant is 0. So that's our general rule for writing down the antiderivative of a function. So the most general one is this one here, writing down some constant c. Now, in some cases, we just won't know what c is, and we're happy to walk away from the problem saying this is the antiderivative. In other cases, we might know something about this antiderivative function, like capital F of 0 is equal to 1, perhaps, right? If we know something like that, sometimes called an initial condition, right, for the function, well, then we could actually probably solve for this constant. So we'll see that in an example or two in this section as well. Okay, so just to try some of these, right? They're kind of nice, especially when we stay down at the lower level, the elementary level. Antiderivatives are a big part of calculus. They're essentially the other half of calculus in terms of single variable calculus. And there's sort of the partner to differentiation, and we'll see more of that in the next chapter. But the basics aren't so bad. The more complicated stuff is unfortunately harder than differentiation. And anybody going to Calc 2 will learn that soon enough. So let's go through the basic ones. F of x equals cosine x. What's the antiderivative of this function? So the game is this. We have to think of a function whose derivative is cosine of x. Well, it doesn't take you long to remember sine and cosine are paired together. And you could write this down. I recommend just write sine of x down. And before you commit it as your answer and box it up, just think about it. Is the derivative of the thing I'm writing down equal to this function? And yes, the derivative of sine of x is cosine x. So I'm happy with that. And then to write down the most general antiderivative, I'll put a plus c, right? I add this constant, this arbitrary constant, this unknown constant, whose derivative is 0. But yeah, so when I take this, the derivative of all this thing goes to 0, and this becomes cosine x. There we have it. What's the antiderivative of 1 over x? This is almost a quiz, but in reverse, right? We'd ask ourselves, what's the derivative of natural log of x? And we'd land here at 1 over x. Well, the derivative or the antiderivative of 1 over x is natural log x. As soon as I write that down, I think it through and say, is the derivative of this function equal to this? And if that checks out, I'm happy with that. And I'll add plus c, and here's my answer. Okay, a little bit more general. I talked about this and maybe specifics of x squared minus 5 or 2x minus 5 in the previous example that we looked at, or the opening example. But if we thought hard enough about this, we'd realize, okay, the antiderivative of this function, we're going to increase the exponent by 1, positive 1. And notice this isn't the case when n is negative 1. Because what is this thing when n is negative 1, by the way? It's 1 over x. And we just saw above that thing's antiderivative is natural log of x, or we just recalled that, basically. So that's the only place this isn't true. And of course, that wouldn't make sense. If that was negative 1, we'd add 1 to it, we'd have x to the 0. We'd be saying that the derivative of x to the negative 1, or the antiderivative of x to the negative 1 is a constant, when in fact we know that natural log's derivative is 1 over x, which means that 1 over x's antiderivative is natural log. Think that through and make sure that makes sense. Nonetheless, we know that this increases by 1. N plus 1 is going to be the result for an antiderivative, right? Now, remember, if we were here, though, and I would probably write this down first, formulating this answer, and I'd say, okay, if I took the derivative of this, I would have a factor of n plus 1 come down and multiply by my coefficient. And since I need a 1 here, well, I need that n plus 1 to cancel. So it would cancel if it multiplied against a 1 over n plus 1. And essentially, we've just formulated the antiderivative rule for any power function, x to the n. So any x to the n, x to the 4th, x to the 1/3, x to the pi, whatever it might be, we can use this formula to find its antiderivative. That's really nice, right? And then, of course, add plus c to make it as general as possible. And you can check that the derivative of this function with respect to x is, in fact, x to the n. Maybe a little bit more intuitive would be an example off to the right here. If little g of x is equal to x cubed, then its antiderivative is, look at this, I've raised this to the 4th, and I've divided by that new power in the coefficient. And that's all there is to it. And then you can check once you write this down. This is the nicest part about antiderivatives, is checking them is easy. If I take the derivative of this, do I get this back? Well, I'll give you a minute to do that, but you should see that it does. But we will. So continuing on, what's the antiderivative of secant squared of x? Well, it might take a little bit longer to think about. You just have to go through the catalog of derivatives of trigonometric functions in your head, or maybe check the textbook, and you'd remember that, oh, tangent x's derivative is secant squared x. And of course, again, we add a plus c to be sure of that. If you ever forget this one, right, this connection, and you wrote that down thinking it was the antiderivative of secant squared x, and you couldn't quite remember what its derivative was, for whatever reason, you could always use the quotient rule, sine x over cosine x, derivative of that, to figure out that in fact is secant squared x is its derivative. So there we are. So let's get a little bit more interesting, and let's use some of these initial conditions. So it says find the antiderivative that satisfies the given condition. So we want an antiderivative of this function that satisfies this given condition here. I might slip and call it an initial condition. Typically, initial condition means that this value is a 0. And what we're talking about is we're starting something at a time t equals 0 or something depends on time. We start at 0. Nonetheless, it's a condition, and we can use it to determine values of c. First things first, we pick up our function, little f of x, lowercase f of x. It's 4x cubed minus x squared. I want to find its antiderivative, and we just saw a really nice power rule for finding antiderivatives. So here's 4x cubed. I know that the x cubed is going to become x to the 4th, and I know that I need to have a 1/4 in there for that 4 to cancel if I were to take the derivative, right? The 4 times the 1/4 should cancel and leave me with just x cubed. This 4 here is just the constant coefficient, right, of this function. So I'm just going to leave it out front when I do this work. So what I really do is factor the 4 out, more or less, and put in brackets the place where I want to write down x cubed's antiderivative. And then I work it through. I add 1 to 3 to get x to the 4th, and then divide by that new power. It's really that simple. So then minus, and in brackets, I'll work on x squared. And on x squared, I say, okay, bring its power to x cubed, and then divide by that new power, 1/3 there. So, and then add plus c, because that's my general antiderivative, some unknown constant c. Only now, this condition will help us determine what c is explicitly as a number. And that's really just a matter of solving for c when we plug in the correct values. So this condition, right, so here's our overall function, antiderivative. We determine c, we do so by writing down our condition, right? 0 is equal to f of 2. So I'm going to plug 2 into this function. Well, it's not going to replace c, it's only going to replace x, right? So we have 2 to the 4th minus 1/3 2 cubed. It's honoring this formula right here. And when I work that out, it looks like we have 0 on the left is equal to 16 minus 8/3 plus c. And working a little further along, it looks like I'll solve for c and get 8/3 minus 48 over 3. And then it ends up being negative 40 over 3. So c is equal to negative 40 over 3. This is just nothing but solving a linear equation, and that's all that's going to happen after we evaluate the function at this given value each time. We'll just solve for c in that linear equation. And when we're done, we update c by replacing it with the known value now that's implied by the condition. And there's our answer to this. There's our specific antiderivative for this function with this given condition here. This will feel a little bit like a physics problem, possibly, and it should. We'll see something similar to that, or something along those lines in our last example here. Next up, find the antiderivative that satisfies the given conditions. So we can have more than one condition, and just like we could find two derivatives, well, we can find multiple antiderivatives as well. So we have f of 0 is 4, f prime of 0 is 12 for this function, and the function that's actually given is f double prime of x. We're given the second derivative of a function. So let's see how we go about doing this. Let's be careful with it. So let's move up a level from f double prime of x. So we're going to back up to f prime of x, to the first derivative. So we take one antiderivative of this function, and doing that, negative 2 gets a factor of an x, right? Again, think about going backwards to check that. Now let's see. 12x, its antiderivative is 6x squared. Again, what I do is this. I say x, I'm going to raise that power to 2. I'm going to add 1 to it, and then divide by that value of 2. 12 over 2 is 6. Right? We do something very similar to get the antiderivative of negative 12x squared as negative 4x cubed. And then plus c1. It's our first constant. So we don't know what it is. So I gave it a name c1 because I know I'm going to have another one because I'm going to take the antiderivative of this function in a moment. Maybe I call it c and then call the next one c1, but this is just how I've done this problem. So next up, we need to get f of x, right? We have f prime of x. So I'll do all the same steps I did to this one, or this one, f double prime, I'll do the same steps to f prime to get f. So negative 2x has antiderivative negative x squared. And then the other two, or sorry, three follow in suit, right? Let me point out this one, C1. C1 is a constant. It's times x to the 0. Add 1 to x's power. And we have x to the first power. Divide by 1, and we still have C1 times x to the first power. So that's what happens to that constant when we find its antiderivative. And then we introduce yet a new constant, C2. When we get here, it's probably not a bad idea to make sure that this antiderivative is in fact correct. In other words, take two derivatives of this function and make sure you get back this function. That's a great way to check that you're on the right path. Then you'll proceed to say, okay, let me use my two conditions to determine my two constants. So here we are working on that. We know that 12 is equal to f prime of 0. Right? Now, it doesn't really matter which of these I solve first. I could use 4 equals f of 0 and solve for C2 first. It's really either way. But since I know f prime and it's right here and easy to write down, I'm just going to start with that one. And well, if I plug in 0 to f prime, well, what happens? All of these terms drop out as 0, and I'm just left with the C1 on the right-hand side. And all of that is equal to 12, thanks to f prime of 0 being 12. So I know that C1 is simply 12. So there we have it. C1's 12. And what I can do at this point is update my equation. F prime of x is this. Okay. And or I can go back over to here to the function, the total antiderivative that I found, and say, well, this is C1 in this case is a 12. So f of x looks like this expression, which is even better. Okay. Now, I guess one split in the path here that might have worked for us is we could have done this way. We could have found this antiderivative, then found C1, then written this in as is, and then taken its antiderivative and never had to deal with two different constants at the same time in here. So that's the other workflow, other way we could have done this if we wanted to. Either way is fine. So we arrive at this, and we're ready to find C2 by finding our initial condition for f. Well, f of 0 is 4. So 4 is equal to f of 0, and I plug in a 0 for x for all of these, and I'm only left with the C2. So I know that C2 is equal to 4. And now I update everything for f of x, and this is my antiderivative f of x. And again, this is worth checking when you're done to make sure that the derivative of this function, or two derivatives of this function, equal what we started with. You could even check to make sure that it satisfies both the initial conditions. So there it is. Those are just basic antiderivatives. It's not too hard, especially when we're dealing with polynomials, but it quickly will become difficult later on. Luckily, we've got some geometry to deal with in chapter 5 before we see anything too difficult in the course. But lastly, one more situation to look at is rectilinear motion. And this is where we're talking about a function that has position function s of t, where s is distance from a given point known as the origin, and t is time. The velocity function v of t was, remember, that was s prime of t. It was the derivative of s with respect to t. And we had the acceleration function a of t. That was the second derivative of the position function with respect to t. So if we assume that everything is differentiable here, right? And these things only existed if s was differentiable twice anyway. Typically in physics, what we know first is we know the forces acting on an object or whatever, a point mass or whatever it is we might be interested in. If you think about, the ways that Newton's laws of gravity are formulated, we know things about accelerations, the way that forces act on each other. So what we really talk about in terms of physical laws are accelerations. So this is really the more forward direction when you think about a physical setting, something like kinematics in physics. So this is a nice application of antiderivatives here. Okay, so for problems regarding Earth's gravitation, by the way, throughout this section, we'll estimate the acceleration due to gravity near the surface of the Earth as 9.8 meters per second squared, or whenever necessary, 32 feet per second squared, if we're going to work in units of feet. So we're going back to this example of throwing a ball upward with a speed of 64 feet per second from the top of the stratosphere, which is about 1,200 feet above the ground. So it looks like we're working with feet. We have an initial velocity of 64 feet per second. That's what that represents, right? Feet per second. We can see that has a speed, right? Or velocity in this case, because we're throwing it upward. So it'll be positive 64. And then notice our position. It starts 1,200 feet above the ground. So S of 0 is 1,200. S prime of 0, the derivative, the velocity, is 64. So let's keep these two things in mind, right? Again, we wrote a frame of reference here. The ground is when S is equal to 0. So a height up here of 1,200 is positive 1,200 at the top of the tower. What we want to know is find the height of the ball above the ground t seconds later. So we want to find our position function, S of t, of course, as a function of time, t. Well, we're on Earth because we're on the stratosphere, right? So the acceleration due to gravity, this ball, is the following, negative 32, right? So we can start there. That's good to know, right? So now we integrate this one time, and we'll get S, no, I'm sorry, I said integrate. Let's find the antiderivative of S double prime. All right, to use that language. That's going to give us S prime, that antiderivative, and we recall that S prime is the velocity function, V of t. So that's what we're up to now. When we find the antiderivative of negative 32, well, that's just a constant, so its antiderivative is negative 32t plus some constant. And now just a little cleverly, I thought about this as, well, this is V of t, so I'll call this V0, my initial velocity, right? When time t equals 0, I'm moving at a velocity of V0. Well, how fast is this ball moving at time t equals 0? The problem tells us that, right? We've already mentioned that it's moving 64 feet per second. That's its initial velocity. So here it is. 64 is equal to V of 0, and that's negative 32 times 0 plus V0. So it looks like V0 is entered as 64. So we're able to fill in this information and update our velocity function of time as negative 32t plus 64. Okay, so again, look how this problem starts. We start with the acceleration or the forces acting on the ball, right? It's being accelerated due to gravity at negative 32 feet per second squared. Okay, and now we're able to build from that a velocity function. Well, ultimately, we want the position function. This height of the ball is the S of t function that we're looking for. So I need to find the antiderivative of this function now. And I'll do that quite simply, right? T squared now, divide negative 32 by 2, and I get negative 16. I'll have 64t to the 1 power, which is this now, right? And then plus some constant. And now I'm at S of t, so I'll call that constant S sub 0. Again, you don't have to be so slick with the notation if that's considered slick at all, but it's just nice to do that. So this indicates this is an initial position. And we can go back and realize, okay, we were at the top of the stratosphere when we threw this ball upward, and we were at 1,200 feet was where this thing started at. So there it is. Our initial position is 1,200 feet. So our position function for any given time t is this thing right here. Okay. And the next question is, when does this ball reach maximum height? That's fun, right? We haven't really gone back to this since we talked about optimization. Well, how do I know when we're at a maximum height? Well, I'm probably going to look for a local maximum, right? And I'll check my endpoints. Maybe I need to know when the thing hits the ground. That's down below, so we'll talk about that in a moment. But let's see. Let's think about this function real quick before we talk about whether or not it actually has a maximum. And actually, let me use the explicit one that we have right here. Have a quick look. This is a parabola, right? T squared, t, and a constant. All right, we have a negative coefficient in front of t squared. So this parabola opens downward. In other words, it's shaped like this. So the height function of this thing moves along a graph that looks like this. Now the ball itself just moves up and down. It's not moving in a parabolic arc, but if this is time on the horizontal axis and this is height s on the vertical axis, then this is its time in position graph. So somewhere it does have a local maximum, or it has a maximum height that it's going to achieve. So how do we find it? Well, of course, that horizontal line I just dashed in the highlighter there tells us where to do that. We take the derivative s prime of t and set it equal to 0. Well, we know s prime of t back here. We don't have to do much work. I'll just pick that thing up and set it equal to 0. That's exactly what we've done here. I solve for t. That's only a linear equation. Shouldn't be too hard to do. And I see that t is equal to 2. And since our initial units were negative 32 feet per second squared, I know that our time is in seconds. So t is 2 seconds. There we have it. At 2 seconds, the ball has reached its maximum height, and then after that, it's traveling down to the ground. Third question it asks, when does the ball hit the ground? Well, you have to think through what this formula tells us. How's that represented by our position function? Well, that's when the position of the ball is 0. Down here on the ground is when we're at 0. Okay. So we solve for s of t equals 0, and s of t is this function, set it equal to 0. This takes a little bit more work, a little bit more algebra, right? It looks like I first simplified this by dividing by, it was like a -4, and then I realized I could divide by another negative or +4. So I did that to get to this line. And now it looks like I'm ready, probably for the quadratic formula would be the easiest thing to do here, right? So opposite of b will be a 4. So we'll start with that. Opposite of b plus or minus the square root of b squared. So 4 squared, 16, minus 4, part of the formula, times a, which is 1, the coefficient of t squared, times -75, which is c, our third term in the trinomial, all divided by 2 times a, and a is 1. Okay, and then we work out the rest of the details here. It looks like we have a positive root, so that's a good thing, right? At least a positive number in the radical. So that'll evaluate. We actually do have real values, and we do expect there to be at least one t-value that satisfies this, right? Because the ball, after all, should hit the ground if this is a working model of reality. And it looks like 4 plus or minus 2 root 79 is a simplification we did here. That's fine. You could have gone to a calculator at this point, potentially. Let's see. And when we simplify this, we actually have 2 plus or minus root 79. We'll take a close look at this. Negative root 79 is between 8 and 9. 2 minus a number between 8 and 9 is negative. That would be a negative time t. That one's out, right? We're not moving backwards in time. We're only moving forwards in time, so we need a positive time. Luckily, 2 plus root 79 is positive, so I take that to be the time when the ball hits the ground. Incidentally, the other side of this, that negative time one, actually is, remember that this thing's a parabola and it opens downward, and maybe I'll draw something like, I suppose it goes upward here first and then drops, right? Over here somewhere, this is that artifact in the model that's at a negative time where it's going to be on the ground. But again, that's useless to us because we don't travel in that direction. We only travel forward in time on this parabola. The ball goes up for a bit. At this time, it's at its peak, and then it goes on and hits the ground at this other time that we just found. So there it is. Antiderivatives as they apply to basic kinematic equations and simple models in physics.